Okay, so for FRQ number 3, we have a object that has a mass of 20 kilograms, and it will slide down a frictionless plane inclined at an angle of 30 degrees. This at the bottom there is a spring that has a spring constant of 200 newtons divided by meters, and when the block reaches the bottom, it will compress the spring to a certain point. So part A wants us to determine the speed of the block just before it hits the spring. So essentially what we want to find is the speed of the block right here. Okay, so to do this, we first need to find the acceleration of the block as it slides down. So we're gonna have to use newtons for this. So the total force is gonna be equal to mass times acceleration. So the total force this way is just going to be FGX. And since there's no friction, there is nothing opposing it. So FGX is equal to MA. FGX is defined as mass times g times sine of this angle right here. So which I'm gonna call theta, and that's gonna be equal to mass times acceleration. So we have m's on both sides, and we can cancel them out. And by doing that, we've isolated for A. So A, now we can plug in our numbers. So G is 9.8 meters per second squared. The angle is 30 degrees. And plugging this into the calculator, we get 4.9 meters squared. So that is our acceleration down the incline. So now that we have our acceleration, we can find our velocity at this point using this kinematic equation. Vf squared minus Vi squared is equal to 2 times the acceleration times the distance traveled. So in this scenario, when the block is right here, the velocity is 0, so the initial velocity will be 0, and this term will cancel out. So what we will have is Vf squared is equal to 2 times acceleration times distance. We're trying to solve for Vf, so we square root both sides. Vf is going to be equal to square root of 2 times acceleration times distance. And now we plug in our numbers. So 2 times our acceleration we found right here is 4.9 meters per second squared. The distance traveled is given right here, 6 meters. And then plugging this into the calculator, we get 7.668 meters per second. So that is our speed of the block at this point. Okay, part B wants us to calculate the time it takes for the mass to travel 6 meters. So essentially how much time it takes for a block to move from here to here. To do that, we can use this kinematic equation. Distance traveled is going to be equal to the initial velocity times time plus 1/2 times acceleration times t squared. So now we can just plug in our numbers since we have everything. Our distance travel, of course, is 6 meters. Our Vi, as I said before, is up here. There is no initial velocity, so this is going to turn out 0. So this term is going to cancel out. Our acceleration we found up here is 4.9 meters per second squared. And time is what we're trying to solve for, so t squared. So if we want to solve for time, we're going to have to isolate for it. And to do that, we're going to times 2 over, divide by 4.9 and square root everything. So time is going to be equal to 6 right here. Then multiply by 2. Multiply this 2 over. Then divide by 4.9. And square root everything. Plugging this into the calculator, we're going to get 1.565 seconds. So that is how much time it takes for the block to travel 6 meters. Part C wants us to determine the distance the spring has compressed when the block when the block comes to rest. So essentially how much the spring will compress when before it starts going back up. So to do this, we need to know our potential energies, because those are essentially our total energies from each point. So the total energy initially is going to be equal to your potential energy initially, because that's all you have at this point, and that's going to be mghi. Now we don't know our h, and so I'm going to draw a visual to help us find it. So this is our incline. So there's 6 meters we're going to travel, and we're going to compress a distance of, I'm going to call it x. So the h will be this height right here, and to find this height, this is basically a triangle. So taking sine of this angle right here, sine of 30, we're gonna get, so it's opposite over hypotenuse. So opposite over hypotenuse. So it's gonna be hi over x plus 6 right here. So if we want to solve for hi, we're gonna times this over. So essentially our hi is gonna be equal to x plus 6 sine theta. And so if we plug this into our equation, our PEI, or our total energy initially, is going to be equal to mg times x plus 6 times sine of theta. Sorry for that messy word, but yeah, here you go. Now our energy final at the bottom is gonna be just equal to the potential energy of the spring, because the object has stopped moving and all energies have been converted to just a spring. So it's gonna be equal to 1/2 kx squared. So x is the distance compressed. So now that we have this, just make this clear. This is PE spring, and the equation for PE spring is 1/2 kx squared. Okay, so now that we have this, we just need to set the energies equal and solve for x. So energy I is equal to energy final and then we plug in this formula and this formula. So our initial total energy is mg times x plus 6 sine theta. Our energy final is this 1/2 kx squared. We have everything, so all we need to do is plug in our numbers. So okay, our mass is 20 kilograms. Gravity is 9.8 meters per second squared. X is what we're trying to solve for, and this is 6 meters. Sine of our angle is 30 degrees, and this is going to be equal to 1/2. The constant given was 200 newtons divided by meters, and x is what we're trying to solve for, so x squared. So simplifying this number down, we're going to get 98 times x plus 6, and simplifying this side down, we're going to get 100 x squared. So I'm going to distribute this 98 to terms in here, so we're going to get 98x plus 588, and that's going to be equal to 100 x squared. Now this we're going to add to one side. I want to keep this positive, so I'm going to subtract on both these two to the side. So what we're going to get is 0. It's going to be equal to 100 x squared minus 98x minus 588. And then we use the quadratic formula to solve for this. And so we're going to get x is going to be equal to 2.964 meters. Now I got two answers for the quadratic formula, but I'm choosing the positive one, so this is my answer right here. Okay, so that is the distance compressed. Part D wants us to justify if the maximum speed occurs at when the block strikes the spring. So is this the maximum speed that the block is going to attain? My answer is no. And this is because after the block strikes the spring, there will be the acceleration will decrease, but it will still be greater than 0 until the spring compresses to a point when F spring is greater than Fgx. So I'm gonna write that for you to visually see. So the acceleration will decrease, but will still be greater than 0 until the spring compresses to a point when F spring is greater than Fgx. Okay, so since since acceleration will still be greater than 0, that means the block will still be gaining speed. And so that means that there will be no so that means that the maximum speed will be attained after the block has touched the string. So that's what I'm gonna write. Since the acceleration is still So since the acceleration is still greater than 0 after striking the spring, the block will still gain speed for a while after striking the spring, and therefore the block will attain a higher speed after striking the spring. Sorry for the slow thing, but this is what you asked for. Okay, so part E, it asks to justify if the answers for part A, B, and C will change if the mass is increased to 40 kilograms instead of from initially it was 20 kilograms. So, okay, so looking at part A, in our calculation, our masses cancel out. So obviously this is a sign that mass will not come to play in finding acceleration, and if acceleration doesn't change, our velocity won't change either. So my answer for part A is the answer to part A will not change because mass cancels out in the process of solving for acceleration via Newton's. Okay, so part B, if we take a look at this, since the acceleration does not change at all, since the acceleration for here doesn't change at all, and that's the only variable in this equation that is dependent on mass, that means that our answer won't be changing either. So the answer to part B will not change because the only variable that is dependent on mass in calculation is acceleration, and since acceleration doesn't change, everything will stay the same. Since the acceleration doesn't change, everything will stay the same. Okay, now looking at part C, in our calculation, we did use mass right here, and this one we did not use mass at all. So it looks like if we did increase our mass, nothing will cancel out and our potential energy will actually increase. So there will be a change in the answer. So the answer to part C will change because PEI, which is mg sine mgx plus 6 times sine of theta, depends on mass. And mass does not cancel out in the process of solving for distance compressed. Sorry, my writing is ugly, I know, but don't give us these problems then. Okay, part F, we are asked if there was friction between the blocks on the surface. I mean, between the block and the surface, and if the coefficient of friction was 0.15, we have to recalculate the distance compressed. That is what part C asks for. So we have to recalculate part C. Okay, so again, we're gonna have to set up our statement. Okay, so if there was friction, energy initial is gonna be energy final plus the work loss due to friction, the work done by friction. Okay, so I'm gonna define my work of friction on the side. Work of friction is gonna be equal to Fk times delta x. Now note that, I'm gonna call it this D instead. Fk is mu k times mg times cosine of theta and the times distance. So we have all of this in, we just need to plug in our numbers. So mu k is given to be 0.15, mass is 20 kilograms, g is 9.8 meters per second squared, cosine of 30 degrees, and our distance travel, our distance that the work is gonna do for that friction is gonna do work on is gonna be x plus 6, because there is friction on from here to here. So that is our distance, x plus 6 meters. So simplifying this, we're gonna get 152.767 plus 25.46 x, and this is in terms of joules. Okay, so again, we already defined energy initial earlier. It's the potential energy of the block at the top, and we've already found it up here. It was this whole equation up here. So our total energy initial is mg times x plus 6 times sine of theta. Our energy total final we found up here is equal to our PE spring, and our PE spring is 1/2 kx squared. So it's gonna be 1/2 kx squared, and our work of friction we found right over here. So plus 152.767 plus 25.46 x, and this is in terms of joules. We have everything, so just plug in our numbers. 20 kilograms is our mass. Gravity is 9.8 meters per second squared. This is x plus 6 meters right here. Sine of angle is 30 degrees. Constant was given to be 200 newtons divided by meters. Our x is what we're trying to solve for, so x squared plus this whole thing over here. This is our work of friction. Joules. Okay, so we can simplify this down. So this side, again, same as before, is going to be 98 times x plus 6. This side, same as before, it's going to be 100 x squared. And this, we just rewrite it. So it's going to be plus 152.767 plus 25.46x. Okay. I'm running out of room. So if I, okay, so from here, I'm gonna distribute this out here, these numbers. So we're gonna have 98x plus 588. It's gonna be equal to 100x squared plus 152.767 plus 25.46x. So we're gonna move everything to this side. So we're gonna subtract 98 and 98x and 588. So 0 is gonna be equal to 100x squared. I'm gonna do my x terms first. So this subtract this is gonna be equal to 72.54x. This term subtract 588 is gonna be equal to negative 435.233. Now we use our quadratic formula to solve for x, and our x turns out to be 2.480 meters, and this is the positive answer, so that is our answer.